The topic of this seminar is carboxylic acids and esters. Carboxylic acids are a class of organic compounds containing the carboxylic group. The structure of functional group can be represented in any one of three ways. Nomenclature of carboxylic acids. We derive the UPC name of an acyclic carboxylic acid from the name of the longest carbon chain that contains the carboxyl group. Drop the final letter E from the name of the parent hydrocarbon and replace it with oic acid. Number the chain beginning with the carbon of the carboxyl group. Because the carboxyl carbon is understood to be the first carbon, there is no need to give it a number. To name all side or other functional groups and list them in alphabetical order. Before each name, to use numbers that correspond to the location of the group. Let's to name several structures of carboxylic acids. It is an carboxylic acid with 1, 2, 3, 4, and 5 carbon atoms in chain. The name of parent chain with 5 carbon atoms is pent. There is no pi bond between carbon atoms, so it is saturated carboxylic acid, and that's why we will use suffix A. Then we have to put oic and word acid, so the full name of this structure will be pentanoic acid. Second example, unsaturated carboxylic acid. Again, we have to name main chain as there are 1, 2, 3, 4, 5, 6 carbon atoms in main chain. We will use hex. This compound has pi bond, which is located between third and fourth carbon atom. It is a double bond, it is an in bond, so we will use 3 and suffix in. Then we have to add oic and word acid. So the full name of the structure is hex 3-enoic acid. Hex because there are 6 carbon atoms, 3 because pi bond, double bond, is located between third and fourth carbon atom. Oic and word acid because this structure belongs to acid. When a carboxylic acid also contains an hydroxyl group, we indicate its presence by adding the prefix hydroxy. So let's count number of carbon atoms in main chain. 1, 2, 3, 4, 5. 5 carbon atoms. Chain with 5 carbon atoms has name pent. There is no pi bond, so it is saturated. N. Okay. Then oic and word acid. And the last step, hydroxyl group is position 4 because OH group is attached to fourth carbon atom. When carboxylic acid contains a primary amine NH2 group, we indicate the presence of it by word amine. So let's start from the beginning. Main chain 1, 2, 3, 4, 5, 6 carbon atoms. So it is hex. It is unsaturated carboxylic acid with double bond between third and fourth carbon atom. So it is 3-ene. Then suffix oic and word acid, and the last 5-amino. Why 5? Because amino group is bearing to the fifth carbon atom. This example. As you see, there are two possibilities for organic chain containing carboxyl group. First one with 1 carbon, 2, 3, 4, and 5 carbon atoms. And the second one, 1, 2, 3, 4, 5, 6. Both chains contain carboxyl group, but the second one is the longer organic chain than first one by one carbon atom, so it is our main chain, and name of this chain is hex. There is no pi bond in this chain, so saturated carboxylic acid and suffix A plus oic and what acid. Then to second carbon atom in this main chain, we can see side group with 1, 2, 3 carbon atoms. Side chain with 3 carbon atoms has name propyl, and position for this propyl group in main chain is 2. So full name of this compound is 2-propyl hexanoic acid. Aromatic carboxylic acids. Name of aromatic carboxylic acids is derived from the benzene. As benzene ring is a parent chain, we will use word benz, then we will add oic and word acid. If benzene ring has some side groups or another functional groups, we will list their name according to English alphabets before word benz. For example, this structure with hydroxyl group in second position. We remember that numeration will start from carbon bearing this carboxyl group, so it is benz plus oic and word acid, and the last one position for second group attached to benzene 2-hydroxybenzenoic acid. And to name the carboxylic acid, we add the suffix dioic acid to the name of the parent alkene that contains both carboxyl groups. The numbers of the carboxyl carbons in name are not indicated because they can be only at the ends of the parent chain. For example, this structure with 2 carboxyl groups with 2 carbon atoms is a typical and the simplest decarboxylic acid. So 2 carbon atoms in main chain. Name of this chain is 8. No pi bond plus A and plus dioic and what acid to show that it is dioic acid. In parentheses, you can see common name of this acid, oxalic acid. Oxalic acid is derived from the one of its source in the biological world plants of the genus Oxalis, one of which is rhubarb. Oxalic acid also occurs in human and animal urine, and calcium oxalate is a major component of kidney stones. Almost the last example is nomenclature of carboxylic acid. So decarboxylic acid with several carbon atoms. Let's to count number of carbon atoms. 1, 2, 3, 4, 5. 5 carbon atoms, no pi bond, plus suffix "-ane", and plus dioic acid. Okay, this structure, this pentyne dioic acid, it is nomenclature name, but also this compound has common name. You can see common name in parentheses, it is glutaric acid. I propose to name this structure without my help, and later we can discuss and we can compare your version with correct systematic name of this structure. So correct numeration order and correct name for this structure. Now I explain why I name it in this way. So compound has 6 carbon atoms. That's why name of main chain is hex. No pi bond between carbon atoms, so plus suffix "a". Dioid, because compound has two carboxylic groups. Also, this compound has two groups attached to main chain, one functional group hydroxy group and one side group ethyl group. We have to list their name according to English alphabet. As letter E is close to letter A, so ethyl will be first, followed by hydroxy group. If you start numeration order like me from right to left, position for ethyl is 3, position for hydroxyl group is 4. But if you choose another way, from left to right, we will have position for hydroxyl group 3 and position for ethyl group will be 4. The total sum for both ways is the same, but for numeration from right to left, position for first locant is lower. That's why this numeration order is correct. I hope most students name this structure correct. Common names of aliphatic carboxylic acids, many of which were known long before the development of IUPAC nomenclature, are often derived from the name of a natural source from which the acid could be isolated. In this table, I listed several aliphatic carboxylic acids structures and their both IUPAC and common names. Also in the last column there is a source from which the acid could be isolated. You can press pause and read more detailed structures, names and source. Chemical properties. Acidity. Carboxylic acids are weak acids. Value of dissociation constant for most unsubstituted aliphatic and aromatic carboxylic acids fall within the range of 10 to the power minus 4 till the 10 to the power minus 5. Substituents offer high electronegativity, especially hydroxyl group chlorine atoms near the carboxyl group increase the acidity of carboxylic acids, often by several orders of magnitude. Electronegative atoms on the carbon adjacent to a carboxyl group increase acidity because they pull electron density away from the H bond in carboxyl group, thereby facilitating ionization of the carboxyl group and making it a stronger acid. Compare, for example, the acidity of acetic acid and chloro substitute acetic acid. As you see, increasing the number of chlorine atoms significantly increase acidity. All carboxylic acids, whether soluble or insoluble in water, react with bases, for example sodium hydroxide, potassium hydroxide, or other strong bases, to form water-soluble salts. In this reaction presented reaction between propanoic acid and sodium hydroxide with formation of salt and water as product of neutralization, acid by hydroxide. Also, carboxylic acids react with sodium bicarbonate or sodium carbonate to form water-soluble sodium salts and carbonic acid, weak acid. This weak acid, carbonic acid, in turn decomposes to give water and carbon dioxide, which evolve as a gas. Also, salts of carboxylic acid can react with more stronger acid, for example hydrochloric acid, with formation of acid and inorganic salt. It is a typical reaction for acid and its salt. And now we have to discuss nomenclature of salts. To name salts of carboxylic acid, We have to know name of acid. I suggest to start from this step for that students who don't have too much experience in organic chemistry. So, for example, first reaction. We had propanoic acid. After neutralization with sodium hydroxide, we obtained salt. So, how to name this salt? Salts of carboxylic acids are named in the same manner as salts of inorganic acids. The cation is named first, and then the anion. Cation sodium and propanoate is anion. So, the name of anion, propanoate, is derived from the name of the carboxylic acid, propanoic acid, by dropping the suffix "ic" in word acid and adding the suffix "ate". Okay, so let's to name this one. First, you can press pause and name that might help. So, to name salt, potassium salt of this acid, we have to name firstly this acid. It is 3-bromobenzoic acid, yes. Bromine atom is attached to third carbon atom. So the potassium salt of this 3-bromobenzoic acid will have name potassium 3-bromobenzoate. So potassium, name of cation, then 3-bromobenzoate is name of anion. Pay attention that I include 3-bromo in the name of anion. Why? Because bromine atom is a part of anion, is bonded to anion part, or acid part. Okay? So if there are several groups in an ion, we will list their name according to English alphabets, but we will present their name in name of anion. Many students make mistake when they put all names, including name of cation and some side groups attached to benzene ring or another organic chains, according to English alphabet. It is completely wrong way. Be attentive, please. The carboxyl group is one of the organic functional groups that is the most resistant to reduction. It is not affected by catalytic reduction by molecular hydrogen that can reduce alkenes to alkanes, or by sodium borohydrate, which reduce aldehydes to primary alcohols and ketones to secondary alcohols. However, lithium aluminum hydride is a very powerful reducing agent which converts carboxylic acid in primary alcohols. Reduction of a carboxyl group with this reagent is commonly carried out in diethyl ether. The initial alcohol, the initial product is aluminum alkoxide, which is then treated with water to give the primary alcohol, and lithium and aluminum hydroxides. These two hydroxides are insoluble in diethyl ether and are removed by filtration. Evaporation of the ether solvent yields the primary alcohol. For example, this carboxylic acid can be reduced with lithium aluminum hydride. As final product, we will have alcohol and two hydroxides. Pay attention that double bond, which is present in acid, will be still present after reduction of carboxylic group. So this reduction process is selective reduction process, and just carboxyl group will be reduced by this reagent. Treatment of a carboxylic acid with an alcohol in the presence of an acid catalyst, most commonly concentrated sulfuric acid, gives an ester. This method of forming an ester is given a special name, Fischer esterification. Acid-catalyzed esterification is a reversible process by controlling the experimental conditions. However, we can use Fischer esterification to prepare esters in high yield. If the alcohol is inexpensive compared with the carboxylic acid. You can use a large excess of the alcohol to drive the equilibrium to the right and achieve a high conversion of carboxylic acid to its ester. Alternatively, we can remove water, one of the products of the reaction, as it forms and drives the equilibrium to the right. Nomenclature of esters. How to name esters. The functional group of an ester is a carbonyl group bonded to oxygen atom. Both IUPAC and common names of esters are derived from the names of the parent carboxylic acid. The alkyl group bonded to oxygen is named first, followed by the name of the acid, in which the suffix "ic" and word acid is replaced with suffix "a". So you can see very high similarity between names of esters and salts of carboxylic acid. In position of cation we will put name of alcohol part. In position of anion we will put derivative of acid part. Let's to name this structure without my help, and in several seconds I will explain how to name this ester. So press pause and name this structure. Okay, so first we have to determine alcohol part and acid part. Alcohol part I highlighted by blue color is bonded to carbonyl group by oxygen atom. Acid part is bonded direct to carbonyl carbon. So as we see, correct name for this structure is propyl 3-ethyl heptanoate, where propyl belongs to alcohol part because there are 3 carbon atoms, so name of this alkyl is propyl. Then acid part has 1, 2, 3, 4, 5, 6, 7 carbon atoms, that's why hept. There is no pi bonds in this chain, so N plus 8 to show that it is esters, and also acid part has some side group with 2 carbon atoms. Name of this group is ethyl and position of this group is 1, 2, 3, 3. That's why full name of this compound is propyl 3-ethyl heptanoate. Esters as flavoring agents. Flavoring agents are the largest class of food additives. At present, more than 1,000 synthetic and natural flavors are available. The majority of these are concentrates or extracts from the material whose flavor is desired. They are often complex mixtures of tens to hundreds of compounds. A number of esters flavoring agents are synthesized industrially. Many have flavors very close to the target flavor, and so adding only one or few of them is sufficient to make ice cream, soft drinks, or candies taste natural. The table shows the structures of a few of the esters used as flavoring agent. You can see structures of these flavoring agents, their IUPAC names, and some natural source where we can find these esters. Fatty acids. Long temperature chain carboxylic acids, most commonly consisting of 12 to 20 carbon. They are derived from the hydrolysis of animal fats, vegetable oils, and the phospholipids of biological membranes, for example. More than 500 different fatty acids have been isolated from various cells and tissues. Given in this table are common names and structural formula for the most abundant fatty acids. The number of carbons in fatty acids and the number of carbon-carbon double bond in its hydrocarbon chain are shown by two numbers separated by a colon. In this notation, for example, mm, oleic acid is designated as 18 colon 1. Fatty acid is 18 carbon chain contains one carbon-carbon double bond. There are several characteristics of the most abundant fatty acids. In higher plants and animals, you can see all of these characteristics. For example, as I told, fatty acids are acids consisting of 12 to 20 carbon atoms. The three most abundant fatty acids in nature are palmitic acid with 6 carbon atoms and no pi bond, stearic acid 18 containing carbon atoms, and unsaturated oleic acid. In most unsaturated fatty acids, the cis isomer predominates, the trans isomer is rare. Unsaturated fatty acids have lower melting points than their saturated counterparts. The greater the degree of unsaturation, the lower melting point. We can compare the last position with our table, for example, um, palmitic acid, yes, with 6 carbon atoms and no pi bonds has melting point 63 degrees. And unsaturated palmitoleic acid with the same number of carbon atoms has melting point 1. Also, melting point is growing when molecular mass is increasing, so the longer organic chain, the higher melting point. Why it's happened? Saturated fatty acids are solids at room temperatures because the regular nature of the hydrocarbon chains allows their molecules to pack together in close parallel alignment. When packed in this manner, the attractive interactions between adjacent hydrocarbon chains London dispersion force are maximized. Also, London dispersion force are weak interactions. The regular packing of hydrocarbon chains allows these forces to operate over a large portion of the chain, ensuring that a considerable amount of energy is needed to separate and melt them. All common cis unsaturated fatty acids are liquids at room temperatures because the cis double bonds interrupt the regular packing of the chains. And the London dispersion force act over only short segment of the chains, so that less energy is required to melt them. The greater the degree of unsaturation, the lower the melting point, because each double bond interrupts the regular part of the fatty acids in molecules. We can check this in so for example, unsaturated carbon atoms with 18 carbons, unsaturated melting point 70, unsaturated with one double bond oleic acid 16, uh, with two double bonds linoleic acid -5, with 3 -11. So as I told, the greater degree of unsaturation, the lower the melting point, because each double bond interrupts the regular packing. Found in living organisms, lipids are a family of substances that are insoluble in water but soluble in polar solvents. and solvents of low polarity such as diethyl glycerol. There are several classifications of lipids. Uh, First, classification by function. Lipids play three major roles in human biochemistry. They store energy within fat cells. They are parts of membranes that separate compartments of aqueous solution from each other, and they serve as chemical messengers. Another classification is classification by structure. We can classify we can classify lipids into four groups. First, simple lipids such as fat and waxes, complex lipid, uh, steroids, and groups of several lipids like prostaglandins, thromboxanes, and leukotrienes. The last two, steroids and prostaglandins, thromboxanes, and leukotrienes, we will study next year in course of biochemistry. Today we will discuss simple, complex lipids. Simple lipids are triglycerides or esters of glycerol and fatty acids. Triglycerides are the most common lipid materials. Also, mono and triglycerides are not infrequent. Triglycerides are complex mixtures. Also, some of molecules contain three identical fatty acids. In most cases, two or three different acids are present. The hydrophobic character of triglycerides is caused by the long hydrocarbon chains of fatty acids. The ester groups, uh, also polar themselves, are buried in a non-polar environment, which makes the triglycerides insoluble in water. Physical properties of triglycerides depend on fatty acid part. Uh, in most cases, in its degree of unsaturation. The physical properties of fatty acids are carried over to the physical properties of the triglycerides. Solid animal fats contains mainly saturated fatty acids, whereas vegetable oils contains high amount of unsaturated fatty acids. So, with some exceptions, fats that come from animals are generally solids at room temperatures, and those from plants or fish are usually liquids. Liquid fats are often called oils, even so they are esters of glycerol just like solid fats and should not be confused with petroleum, which is mostly alkenes. So it is the typical triglyceride formed by uh, glycerol, oleic acid, palmitic acid, and stearic acid. This table shows the average fatty acids content of some common fats and oils. Uh, Note that even solid fats contain some unsaturated acids and that liquid fats contain some saturated acids. Some unsaturated fatty acids, for example linoleic and linolenic acid, are called essential fatty acids because the body cannot synthesize them from precursors. They must therefore be consumed as part of the diet. Also, most vegetable oils contain high amount of unsaturated fatty acids, as you can see from table. Coconut oil, for example, has only a small amount of unsaturated fatty acids. This oil is a liquid not because it contains many double bonds, but because it is rich in lower molecular weight fatty acids, for example, uric acid. We'll take a look. Coconut oil has 45% of uric acid and just 24-25 unsaturated. So around 75% of saturated acids are present in coconut. oil, but because of high percentage of fatty acid with lower molecular weight, this oil has liquid state. This hydrogenation is carried out on a large scale to produce a solid fat. In making such products, manufacturers must be careful not to hydrogenate all of the double bonds, because a fat with no double bonds would be too solid. The food processing industry is taking steps to address these issues. Many food labels specifically call attention to the fact that there are no trans fats in the products. Hydrolysis of fats. Glycerides-brain esters are subject to hydrolysis, which can be carried out with either acids or bases. Acidic condition Acidic hydrolysis is occurred in stomach system where a small portion of hydrochloric acid catalyzes the composition of fats with formation of glycerin and fatty acids. Basic hydrolysis is popular in industry. The base-promoted hydrolysis reaction is called saponification reaction. Saponification of fats and oils produce formation of glycerol and a mixture of fatty acids, salts called salt. Salt has been used for thousands of years, and saponification is one of the oldest known chemical reactions. Natural soaps are most commonly prepared from a blend of a tallow and coconut oil. In the preparation from tallow, the solid fats of cattle are melted with steam, and the tallow layer that forms on the top is removed. The preparation of soaps begins by boiling these triglycerides with sodium hydroxide. The typical reaction in general case are presented in the slide. The resultant soaps contain mainly the sodium salts of palmitic, stearic, and oleic acids from tallow, and the sodium salts of lauric and myristic acids from coconut oil. However, natural soaps have their disadvantage, foremost among which is the fact that they form water-insoluble salts when used in water containing calcium, magnesium, or ferrum ions, so-called hard water. Why it happens? Sodium salts soluble in water as in cell react with, for example, calcium ion cation with formation of insoluble salt in water. That's why micelle formation ability of fatty acids anion is trophies in this case. But essential characteristics of soap chemists recognize could be produced in a molecule containing a sulfonate group instead of carboxylate. For example, calcium, magnesium, and iron salts of alkyl sulfonic acids are much more soluble in water than comparable salts of fatty acids. So this synthetic analog of fatty acids is popular in industry now, and we call them detergents. Uh, from the chemical point, they different by just by functional group, carboxylic group in fatty acids and sulfur group in these detergents, but is discussed only in significant components of fat for fat storage cells. Other kinds of lipids, called complex lipids, are important in a different way. They constitute the main components of membranes. Complex lipids can be classified into two groups. phospholipids, and glycolipids. Glycolipids you will study in biochemistry course in next year. Of course, that guys who passed this biological chemistry. Phospholipids. There are two types. Glycerol phospholipids consist of glycerol fragment, fatty acids, phosphoric acid, and some alcohol, as alcohol can be choline, serine, ethanolamine, or other alcohols. Sphingolipids consist of sphingosine instead of glycerol, one molecule, one fragment of fatty acid, phosphoric acid, and choline. The complex lipid forms the membranes around body cells and around small structures inside the cells. Unsaturated fatty acids are important components of these lipids. Most lipid molecules in the bilayer contains at least one unsaturated fatty acid. The cell membrane separates cell from the external environment and provides selective transport for nutrients and waste products into and out of cells. I have finished this seminar, so I suggest you also to read these topics, carboxylic acids, lipids, in book Bettelheim. I use this book to prepare this lesson. If you have some questions, please send us your questions to our common account. Also, you can find this presentation in PPT format, and there are some questions for home task. So these guys who want to improve your knowledge to try to name structures of carboxylic acid, welcome to do this homework. Thank you for attention. Bye.